Hi there, today we're exploring how pressure is measured using a simple yet effective tool, the manometer. So what exactly is a manometer? A manometer is a U-shaped tube filled with liquid, usually water or mercury, and it measures the pressure by showing how this liquid moves when pressure is applied. The higher the pressure, the more the liquid levels shift. So without further ado, let's see how this works and the physics behind it.
To truly understand how a manometer works, we need to dive into some physics principles, focusing on pressure, fluid statics, and hydrostatics. Let's start with pressure. Pressure P is defined as the force, F, applied per unit area, A, and is given by the formula P equals F divided by A. In the context of a manometer, we're particularly interested in how pressure affects a fluid, which leads us to Pascal's principle. Pascal's principle states that any change in pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid. This is why when pressure is applied to one side of the manometer, the liquid responds by shifting in both columns. In a manometer, we have two pressures to consider, P1 on one side and P2 on the other. The difference between these pressures, delta P, causes a liquid to move and is given by delta P is equal to P1 minus P2. But how do we relate this pressure difference to the height of the liquid? This is where hydrostatic pressure comes in. Hydrostatic pressure is the pressure exerted by a fluid due to its weight, and in a manometer, it's directly related to the height difference, h, between the liquid columns. The relationship is described by this equation. Delta P is equal to rho, which is the density of the liquid, times g, which is the gravitational acceleration, times h, which is the height difference between the two liquid levels. The manometer typically measures gauge pressure, the pressure relative to atmospheric pressure, using the equation P is equal to rho times g times h. If you need absolute pressure, which includes atmospheric pressure, you should use P absolute is equal to P gauge plus P atmosphere. Here, P atmosphere is the atmospheric pressure, which is typically around 101.3 kilopascals at sea level. So to sum it up, when you apply a pressure P1 greater than P2, the liquid in the manometer shifts, creating a height difference h. This difference corresponds to the pressure difference, delta P, between the two sides, as described by our equation delta P is equal to rho times g times h. By measuring h and knowing rho and g, you can calculate the exact pressure difference in the system.
Now let's discuss the materials you'll need, and I've got two options for you, one if you have a 3D printer and one if you don't. If you don't have a 3D printer, no worries. You'll need a plank of wood, a rubber tube, some water mixed with food dye, zip ties and a syringe. First, drill a few holes in the plank to secure the rubber tube in place using the zip ties. Once that's done, we're almost there. To complete the setup, fill the tube with the dyed water and attach the syringe, and just like that, your manometer is ready to go.
Or you have a 3D printer and can do this. Okay, so the 3D printer is going to take a while, but with some editing magic, it's done. So now we will start by getting our 3D printed piece and a clear rubber tube. And now we will use the rubber tube and place it into the grooves which we printed into our piece over here. And it should look something like this. You can see that the tube is pretty straight and we have all these water markings like this. Next step would be to put a syringe in on one of the sides. This is for our control. Usually you would place this in a place where you would want to measure the pressure. So one side is open to the atmosphere and one side is where we measure the difference in pressure. In this case, as we don't have anything to measure, we will be using a syringe. And bam, it is in. The next step is kind of difficult, and it will require us to turn this whole If you're having troubles keeping the pipe in place, the tube in place while lifting it up, see it became loose, what you could do is grab some transparent tape, like the one we have here, and just tape some parts of the tube into place. Over here, we can add a piece of tape. On the other side, we could add a piece of tape. And at the very bottom, we can add another piece of tape. And now it should be more tightly secured in place. So when we lift it up, it should not leave as easily as it usually did. Now we will set it up upright in the location where we want to keep it. And in this case, it's just popped up to this wall. And here we will use this blue water that we dyed using blue coloring dye, and place a bit of water into the tube. We will be using the syringe as it facilitates putting the water, but if you don't have a syringe and you're just measuring it out in some other location, you could use a funnel to fill it up. So let's just put a little bit of water. Keep in mind that this tube is very thin, so just a slight bit of water should be enough. After a bit of mixing, you can see that the water is now level at this point over here. And now you're basically done. The experiment would go as follows. This tube here is open to atmospheric pressure, and this one would be connected to where we want to measure the pressure difference. And in this case, we will be using the syringe. Now the syringe is very huge. I would not recommend using one this big. So even the slightest difference, if we push it a bit in, you will see that there will be a big difference over here. So let me demonstrate. I will start pushing now. And let's say that's the pressure difference. Now you can clearly see that the water level up here is higher than the one over here. This is caused by this area here having a much higher pressure than atmospheric pressure. Well, when I say much higher, we will calculate that later.
So the blue line is where the liquid originally was at, and the red lines are marking where they are currently. You need to find the difference between both red lines and the blue line. So on the right, we can see that it increased by 2, and on the left, it decreased by 0.5. So our height difference is 2.5. Now we plug that into our formula, which is rho GH, H being 0.025 meters, G 9.81, and rho is just 997 kilograms per meter cubed. And we have to add the atmospheric pressure onto that, and that's our final pressure.
Now, I was just clearing it up and I saw that this was happening, and I think it's very important to know. As you can see here, the tube over here is still under pressure. However, the water level has leveled out basically. This means that there's a leak in our system, most likely coming from here. This is allowing some air to escape so that the pressure changes again. So to make sure that this doesn't happen in the real contraption that you're going to use to, for example, measuring a propane tank, you should always make sure that you have a seal. And to guarantee a seal, you can use any type of material to seal it. For example, hot glue is a really good sealant that you might have at home, or you can have any professional grade sealant. So yeah, I just wanted to say that.
Now that you've seen how easy it is to build your own manometer, I encourage you to give it a try. Experiment with different liquids, test various pressure sources, and see how the principles we discussed come to life in your own setup. It's a fantastic way to deepen your understanding of pressure, fluid dynamics, and the fascinating world of physics. And if you enjoyed this video, don't forget to hit that like button and subscribe to the channel. By subscribing, you'll stay up to date with more exciting experiments, tutorials, and deep dives into the science behind everyday phenomena. Thanks for watching and happy experimenting!